So, good morning. Remote people, do you hear me?
Yes, Professor.
Okay, fine. Mhm. Okay, let's go ahead. In the last session, oh, 1 second. Yes, in the last session, we have started to see new substrate types. Substrates are extremely important because the substrate technology mainly determines how the following steps of fabrication have to be accomplished. And also substrate technology is very important for wiring density, for reliability, for the temperature limits of electronics, and also for the power dissipation that the electronics can tolerate. So all of these are performance parameters which have to be taken into account. And we saw ceramic substrate technologies. And that's a very fine example. It's a typical automotive electronics example, exhibiting an ASIC, exhibiting some special circuit in order to achieve, let's say, customer specific properties. And in order to have high reliability, here we have gold conductors, gold wires. And we can also see that the pitch of these interconnections is very small. It's of course bigger than let's say the diameter of these bonding wires, but it is still let's say near the pitch that can be accomplished on the chip itself. So that is a technology for combining several highly integrated chips on one substrate without having a package for each individual chip. Okay, then we have seen that these substrates have a special build-up, and that build-up is first of all, of course, metallization, having the conductors, but we have more functional layers like dielectric, which insulates individual conductor tracks which are on top of each other. Another important feature is that we do not have explicit wires, vias, but we have an overlapping of conductors, and in that way we can come from layer to layer. And yes, we have already seen for the bonding pads or the areas around the bonding pads, we have gold. And another thing that is important is a resistor that is integral part of the substrate, it can dissipate more heat, or maybe it's better to say for a certain heat, it dissipates, it is less increased in temperature. And as all resistors are temperature dependent, it's a good method or a good strategy to achieve high precision resistors. Of course, the material is also important, as we will still see in this lecture. That is an example that was provided by the DuPont company, who was in the 1990s and maybe also in the 2000s or so, the leading company, and is still leading in the field of materials for thick film technology. And they showed that technology in order to make multi-layers, but we can also see how many individual layers do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 on one side, and let's say 10 on the other side. That means 25 different layers, and each layer is produced individually. That means it is printed, it is fired. It is printed, it is fired, and that is repeated 25 times. And each cycle takes, at least in the oven, takes half an hour. And that means 25 times half an hour. It's 12 hours just in the oven for such a circuit. Do you think that's a good method? What's the temperature of such an oven? Yes, it is 850 degrees centigrade, and that means it takes much more power to operate it than your kitchen stove has. Yes, and that means lots of energy is you could say needed. I would not like to say wasted here. It's needed just to do that, and that's one of the. And there are two strategies to overcome this. One strategy is having a higher wiring density, so you need less wire, less layers, yeah, just more conductors on one layer. And the second is just use another technology. Also, that's a reason why people in some applications go towards high performance printed wiring boards. Okay, so we have also seen the most important properties. And first of all, of course, it's important to have the electrical properties like permittivity, dielectric loss factor, and also dielectric strength. Another property that is important is the CTE when we want to mount a chip, because when the substrate has a high CTE and the chip always has around 3 ppm per Kelvin, then we have a high stress either in operation or just after the production. And that means ceramic substrates are quite good because they have a low CTE mismatch to the chip. Also, the thermal conductivity of some of the ceramic materials is quite good. So it's around 20 to 30 for the alumina substrates, and it is, let's say, 150 to 200 for the aluminum nitride materials. Unfortunately, that almost perfect material, aluminum nitride, has one big disadvantage. And what's that disadvantage? When you talk to industry people, what's the biggest disadvantage a material can have, it's expensive. Yeah. Okay. Especially in mass applications where you produce many. So the next thing is, and that's important maybe to repeat, how such layers are produced. First of all, they are printed, and typically it's a screen printing. So that means you have a screen, that screen has openings, and you press a certain paste through the openings in that screen. So we can see that is the screen where it looks silver, it has openings. So here the stainless steel wires can be seen, and they can be seen here from the different color. So when it's open, you can press the paste through it. And now there was a process of photolithography. And after the last lecture, I found there was a certain misunderstanding. Of course, the photolithography is not made on the substrate. The photolithography is made on the screen. Yeah, that's important. You want to have these openings and this pattern on the screen. And so the screen is coated with a photoresist, then it is exposed, developed, and then you have the openings. And through these openings, you can print the paste by moving this squeegee over the screen, and the screen is positioned over the board. To some of you, that was evidently not clear after the last session, so I thought it would be better to repeat it explicitly. Okay, so in screen printing, in such applications, we can have conductor width or conductor clearance down to 20 micrometers. Unfortunately, the finer the pitch is, the higher is the probability that we have that we do some mistake in the printing, and then we have some printing defect. Yeah. For instance, you can create a bridge, and that means two conductors are connected in one location, and that means we have a short circuit, and typically that cannot be repaired. So in such processes, you must be perfect. Okay, then we have the oven. We print. The ink or the paste is still wet, then it is first dried. Next step is the burnout section. Anything that is polymer, for instance, or organic material is burned out. So it's really burning away. And only after that, let's say purification, we only have the metal powder remaining, and then it is sintered, you could say, at 850 degrees centigrade. So, of course, you must not cool such ceramic substrates too fast after the firing, or they might crack, because ceramics are brittle, and also in that way you can generate defects either in the substrate, or if you have a glass layer on it, possibly that glass can crack. Okay, that is just such a firing profile with a well-defined rate, keeping it for a time, for instance, 10 to 12 minutes, cooling down at a certain rate. And that is just an example for the firing step. Now, question is, which materials can be used for printing? We have already seen when we produce ceramic high temperature packages, we use tungsten or we use molybdenum, which is later on nickel plated. In thick film technology, we do not use these metals because in thick film technology, we use ovens that operate in air. So that means we need a metal that will not oxidize in air. And of course, the noble metals are best suited. And now for noble metals, of course, what are the best available ones? Of course, the best available one is silver. So it's also the cheapest of all noble metals. And so for some layers, silver is used, especially for the first layers we print. What is it? Another advantage of silver? Silver is best at which properties? What are the relevant properties for a conductor? Come on. Sorry? Yes, yes. Let's say better resistivity. Yeah, resistivity is the material property, or in that case, maybe it's a conductor. It's evident conductivity is the property. Yes. On the other hand, resistance is the property of a device. Yes. Resistivity is a specific property of a material. Same with conductance and conductivity. Conductivity is specific, conductance is for a device, inverse of a resistance. Okay, so in that way, conductivity, and both for heat and for electricity, and silver is the best. What is the second best? That's copper. Next to follow with respect to these properties are aluminum and copper and gold, which are also quite good, but only if they are pure metals. If they are alloys, conductivity goes down significantly, often by a factor of 10 or so. So silver palladium is important. It's first of all, it's similar in properties to pure silver, but we do not have that leaching effect. When you have a silver wire and you solder it with a soldering iron, you will notice soldering too long, the wire is gone because it dissolves in the solder. If you have a silver palladium, it takes much longer until it is dissolved, yeah, in the tin. And that's the reason when we solder onto such substrates, we often use silver palladium. On the other hand, it's also better corrosion resistant than pure silver. It's still relatively cheap, and so it is often used even if we do not solder. Then on the surface, when we want to have perfect corrosion resistance, we can use something like gold platinum, gold palladium, or some other alloys using noble metals that are expensive. For such metallizations, there are certain properties that are important. For instance, the adhesion strength. So strength can either be measured in terms of megapascal, which is also always, let's say, a strength or a force per area. But for conductors, sometimes we give the peel strength that you must imagine like you have an adhesive tape put on a surface and you peel it off. And then the force is, of course, the higher, the wider that strip is. Yeah. So in that way, the peel strength is measured in terms of Newton per millimeter. And typical peel strengths of metals, generally in assembly and packaging, are around 1 to several Newton per millimeter tape width. Thickness of such tracks, and that's the name why it's called thick film, is on the order of magnitude of 10 micrometers. So that's when we call it thick film. We call it thin film when it's on the order of magnitude of 1 micrometer or below. Yeah, so it's just as a rule of the thumb. And so typically here it's given 7 to 20, or here 10 to 17. So it's a similar range. And when the resistance is measured for such metallizations, in most cases, the ohms per square is given. So that's the surface resistance. And why don't we give, let's say, first of all, why don't we give the absolute resistance first when we want to specify the properties of that metallization? So why don't we give the resistance, and why don't we give resistivity, but we give surface resistance, or I would think better surface resistivity? Why do we give that property, ohm per square? When you compute resistivity, you need 3 properties. What do you? Yeah, so you make a layer on the surface and you want to know resistivity of that metal. What 3 properties do you have to measure? I want to know the resistivity of the material. So what do 3 properties I need?
Area, length.
Sorry, I didn't understand you.
That is like, what is the area of the material, length of the material, thickness?
Oh, that was hard to hear, but now maybe I say it myself. Of course, when you want to know the resistivity, you need to know the resistance, so ohm meter. You need to know the length. That's also easy. You take a measuring tape and say, okay, 1 centimeter and 10 micrometers. And you need the cross-sectional area. And for a printed layer that is not perfectly perpendicular in shape, it is hard to measure. Yeah. And especially when hybrid technology was introduced, there was hardly any method to measure such an irregular 10 micrometer thick layer precisely. And so what people did is they printed a certain area, and for that area, one square, you have a certain resistance. And for that square also, you can show that it doesn't matter how big the square is. Yes, that's the ohms per square, because when you make the square bigger, it is longer and is also wider. Yeah, and in that way, resistance always keeps constant. So that's why these people typically use ohms per square, because they don't know the cross-sectional area. And in the end, they want to achieve a certain a certain resistance, and so they know the length, they know the width, they don't know the thickness, of course. And if they know the material property, specific resistance or resistivity, then they can predetermine which resistance that will have. Okay, so what is also important is to be able to wire bond. And first of all, the bonding process must be possible, but the second thing is also it must be corrosion resistant after the bonding. So that's why we have different metallizations. Also, what was tried for some time to use copper as a thick film metallization. What is an advantage of using copper contrary to silver? And what is a disadvantage? Yes, cheaper, very good. And what is a disadvantage?
It is corrosion. It can react.
Yes, the disadvantage is copper oxidizes. Copper is not very corrosion resistant, and it is not resistant against high temperature air. And that means in 850 degrees centigrade, which you would also need for sintering, it will just be converted to a black powder that is named copper oxide. Yeah? So it oxidizes. And in that way, you need a shielding gas, and you need a shielding gas of a high quality. Normally, every electronic company has such shielding gas because all companies have a big tank for liquid nitrogen. But again, that is very expensive. And so you have to make a trade-off. Do you want to save nitrogen, or do you want to save noble metals? And in that way, in most cases, noble metals are used in air. So here we see an example that can be very fine layers. For instance, on top of that, we can put a flip chip. Flip chip is well suited because of the low CTE mismatch against that substrate. Another thing is, I already mentioned resistors and why we want to have resistors directly on the substrate. And there are, yes, the question is, what is a property required for a resistor in an electronic circuit? What's the most important property of a resistor? That's one, but not the most important. The first most important property is it must be precise. It must have the value it is specified for. Now we have a problem because almost all materials are dependent on temperature with their specific resistivity. That's depending on whether they have more metallic behavior or whether they have more intrinsic semiconductor behavior. Yeah, so an extrinsic, that means a doped semiconductor is more like a metal conduction, but an intrinsic semiconductor is a semiconductor because the number of carriers is increased with temperature. So such intrinsic semiconductors become better conducting with increasing temperature. Metals, what's the resistance over temperature? Yeah, the resistance will increase with temperature in a metal. So also in a highly doped silicon, resistance will increase with temperature because the carriers are the mobility of the carriers is degraded. Yeah, so that's a metal. It has a constant carrier density, but it has a decreasing mobility. A semiconductor has a decreasing mobility, but the number of carriers is increased more. Yeah, typically it's increased exponentially, while the mobility is decreased linearly. And in that way, we can have a positive or a negative TCR. That's temperature coefficient of resistance. So positive TCR means resistance increases with temperature. Negative means it decreases. So that gives us only little choice with respect to materials which we use for resistors. And on the other hand, also what narrows our choice is that such materials we want to have for resistors must be printed and fired and sintered. Yeah. And in that way, that's not so easy, but material science people find out that we can have some mixed oxides like barium ruthenium oxide or bismuth ruthenium oxide. And these materials have a behavior a little like a semiconductor, a little like a metal, and these effects compensate. And these materials can have a 0 TCR over temperature. That means resistance does not change over temperature. And so for materials, the typical range is something like plus minus 150 ppm per Kelvin. Also, that TCR not only depends on the material, but unfortunately also on the firing process. So that means when you want to have precision resistors, which are printed, fired, you must have a well-defined process that you must not change in order not only to give you the correct resistance, but also to give you the correct TCR, because hybrid circuits or thick film circuits are frequently used in high temperature applications. And that means, let's say normal high temperature means 150 degrees centigrade, advanced means maybe going up to 200 degrees centigrade, and extreme high temperature for electronics is going up to 250 degrees centigrade. So to have a guess. And so going from minus 40 to 250 means a wide range. And as an example, for silver or for copper, also for platinum, the resistance changes by 1%. 1% every 2.5 degrees, you increase the temperature. So that means you have to do something when you want to have a resistor which has an accuracy of 1%, yeah, over the whole range. Or some want resistors that have an accuracy of 0.1%, yeah, under all circumstances, and that is quite demanding. Also, such resistors have some, let's say, certain properties, some peculiarities, like if you overheat them once, they just change their resistance stepwise, and that change is permanent. Or you overload them electrically, also that can lead to a stepwise change in resistance. And in that case, of course, that resistor is damaged. Yeah. So now that means by material selection, we can, and by proper process of firing, we must maintain the TCR. But on the other hand, we simultaneously must address a certain basic resistance, for instance, at room temperature. And now, if you think about such a printing process, printing, firing, and after the firing, you measure resistance, how precise do you think with such a process you can achieve a certain resistance? So I would say the target is 100 kilo ohm. How precise can you be? What do you guess? Maybe easiest you give a percentage. 1 ppm, 1 promille, 1%, 10%, 50%. Just give me a guess. You print. I already said you do not know really how thick it is. Yeah, that's already a disadvantage. How precise can you, for instance, predetermine the thickness of your printing? Oh. It's depending on so many parameters. So if you are good, you can maintain an accuracy of 10% in resistors. So, but you need 1 promille. So what do you have to do when you want to be more precise? You have to trim. Trimming means after production, you measure and then you work on it until it has a proper value. In some way, yes. It's some iterative trial and error process. And but in the end, trial error normally means yes or no. If yes, then, but here it means, okay, 10% or better, and then you improve iteratively. Yeah. No. If you target at 100 ohm, it can be 90 to 110 plus minus 10%. But now, if you have a resistor and you trim it, that means you change the resistance. Can you lower the resistance? Can you increase the resistance? Or can you go in both directions with trimming? Sorry? Yes. So making it higher the resistance means you make it thinner. So some guy from industry one time, he told me, we can just use a razor, go a little over it, take away 0.5 micrometer, and then resistance already increases. Of course, that's not an industrial process, but it shows us, yeah, by taking away thickness, it's easy. How to put on thickness? Impossible. On the length, that could also affect the resistance. You have no chance, yes? The chance is your conductor, you print it. You cannot make it longer. Of course not, because then that would mean, yeah, you can rethink it. Sputter coating means you have to need a local sputtering. First of all, you would need a mask, yes? So what would you do? Take your screen, put it on again, and then sputter through that screen? No. So the trick is first make the resistance too low. Yeah. So let's say the tolerance is 90 to 100. But in your production, you target at 90 to 110. So sorry. Now in your production, you target at, let's say, 85 to 105. Yeah, or still better, you target at 80 to 100. And then when you trim it, you always increase resistance. Again, if resistance is already too high, no chance to modify it. And in that way, we can take away, initially, people were using a micro sandblaster just to, that means rubbing away with shooting sand powder on it. Of course, you do not want to have sand grains in electronics, and so very early lasers were used. So let's say the use of lasers for trimming was one of the first industrial uses of such solid state lasers, already from, let's say, the 1960s or 70s on. Of course, why in that industry, thick film technology was initially mostly for military and aerospace applications, and here it can be expensive, yeah. And lasers were expensive at that time, and on the other hand, it was a very good method. So that's an example of an old system where the circuit is put in, it is lasered, you put it out, you measure it again, you have a certain pattern strategy for lasering it, and then you laser it, do it again. A modern system is a little different. A modern system, first of all, it keeps a constant temperature. So you want to have a good reference temperature. It puts 4 pins for current and voltage on the resistor. And then it measures, and while it measures, material is ablated by the laser until the resistance value is the target value. And in that way, so that's a machinery. You could say it's a laser machine with simultaneous measurement. Here it has a microscope, but nowadays such machinery is mostly fully automated, you could say, and in that way, you don't have a microscope, but you rather have the camera to put it in a pattern recognition system. Okay, so what is important? The cutting pattern. So typically with a laser, you can only make small cuts, yeah, which have a low width, because you don't want to have a 1 kilowatt laser, but you want to have a small laser. And in that way, you make small cuts, but small cuts are sufficient. But having such a cut, is having a disadvantage. So when we look at the current, yeah, we can say the current here, it goes here, it goes here, but that current goes something like. And what does that mean to us? That means here we have an increased current density. And when the current density is increased, what will be also increased? Temperature. That means we get a hot spot here. That's something we do not like later on in the application, because we always want to have the resistor at a uniform temperature. Especially we do not want to have a single hotspot, because that hotspot would limit the maximum operating temperature. And in that way, people worked out different patterns. And if you want to have a really high resistance, you can make such a serpentine pattern. And in that way, you make your conductor narrower and longer. And in that way, you can increase the resistance significantly more than 10%. Yeah? Okay, so that's important. But again, it shows us we always have to take into account how the material reacts. Yeah, and we have a dependency of temperature on current density. Again, if it's hotter, also resistance will be increased. That will still increase temperature locally. And so in that way, these are effects which have to be taken into account. Okay. After we are finished, typically on these resistors, we put on glass as a passivation. The glass is necessary to prevent corrosion. Yeah. Also, it's an oxide; it can still corrode. That barium bismuth or ruthenium, barium ruthenium or barium bismuth oxide can be degraded by humid atmosphere, for instance, so we put a glass on it. Here we see the glass is just fired at 500 degrees centigrade. Why this? The rest of the process was at 850. What could be a reason? Not just, it's more straightforward. I already said when you overheat such a resistor afterwards, it will change its value. And so going to 850 degrees centigrade again, it's like an additional sintering for that resistor alloy. And that means it would, you could be sure it will go down in resistance. And in that way, we take a glass and now 500 degrees centigrade under controlled conditions will not change that resistance value. And in that way, we have as a last step, so-called LT glass, low temperature passivation glass. And that, again, here we can see the typical curve. We heat to a temperature at which organic compounds start to be combusted. When the organics are gone around 400, then we can melt or reflow the glass. And of course, again, we need a limited cooling rate. Okay. Yes, for the temperature profiles you are talking. Yes. Let's say that's just based on experience. Yeah. So all of this has been tried out. Let's say, for instance, the DuPont company, they have a laboratory in North Carolina. And that's their center for development of such materials. And now if they make a new paste, they have to do lots of experiments. And then they try out, and they try out, first of all, on, let's say, on on test patterns, but later on they also have a new customer who wants a new material, and then with them they try out in a real application, and then it is tested, and then people can see if the final product, which is an electronic circuit, has the properties it is expected. And that's one thing, electrical behavior. Second is, do we see defects? And so based on such preliminary development and test phase, such profiles are developed. So it's, of course, such a profile, because I could explain it, is based on a certain, let's say, strategy, which is based on the knowledge of how the materials are expected to behave. Yes, so organics have to be fired out and so on, not too fast cooling to avoid cracks. And so, but all of this is more or less empiric investigation. Yeah. Good question. Okay. So I showed you the initial BlueStack example with 25 layers. And so in fact, DuPont company showed it can be done, but nobody really did it. Yeah, because you, as a production manager, you only get headache from that. And so the DuPont company some time ago, they came up with a new technology, and we have seen the high temperature multi-layer ceramic packages. And now the idea is, what if we develop a low temperature co-fired process? And high temperature meant 1600 degrees centigrade. Low temperature means 850 degrees. So that has to be distinguished. And using low temperature, on the other hand, also use air for firing, makes it significantly cheaper, but again, we need noble metals. On the other hand, the metal systems are already there because it's thick film technology. So the idea was develop a ceramic material that can be sintered, not at 1600, but at 850, together with the firing of the paste. And so that technology was developed. Here, that's an example. Here we see the ceramic layers. It's the typical aluminum oxide layers. It still has a certain porosity. Also, the silver in here has a certain porosity still, but we can see we can make conducting layers, and we can make vias. And so all of the relevant properties we need, or features we need for a multi-layer circuit can be accomplished in that way. So here we can say we have 1, 2, 3, 4, 5, 6 active layers. And on the other hand, in such technology, we have a high wiring density per layer. And so we can produce extremely high wiring density in such substrates. But contrary to that other technology, to just thick film hybrid, here we only have one firing step. Yeah, and that means the energy effort is much lower, and also the time of production is much lower. But we have to have a certain process. Here, that's the scheme again that is modified after some company information by DuPont company. We can see the individual layers. What we can produce, like in printed wiring boards, is buried vias and vias going completely through the material. We have here the stacked vias. The DuPont company also claimed we can put in some material which has a higher permittivity, so we can put in capacitors. Again, that's an option. I don't know about anybody who does that. But what is done is resistors. They claimed we can put in buried resistors, or we can have surface resistors. In the end, I would say what is the relevant technology is surface resistor, and of course that surface resistor again has a low temperature glass passivation in order to protect it. So that's the main features, but here we see, contrary to thick film technology, we have vias which must be produced separately. If we have a ceramic multilayer circuit, how can we produce a via going through that ceramic material and being filled with silver, for instance? How can we produce that? Do you have ideas? So it is hard to imagine that you first produce your circuit, fire it, then you have a ceramic plate, like a kitchen plate, yes, as hard, and then you drill holes. Impossible. It's possible, but the effort is ultimately high. So what you have to do is you have to do the holes in the so-called green tape. So the green tape is the layer here before it is fired. You understood what I mean? No. A ceramic material is first formed before you, like in a pottery, you form the clay, bring it in shape. If you want to make a jug, you must make a hole in it. Yeah. Okay. You do not do it in the fired version, but before firing, you put in the hole. Yeah. Then you fire it, and then you have a fired part with a hole. And it's similar here. And a ceramic material before it is fired is a so-called green material that hasn't anything to do with ecology or so. That's just for 1,000 years, people say it's grünes Material or green material in English language. That's just how to say it. And that's before it is fired. So we have that green material, we put in the holes. These must be filled and then it is fired. So now let's see it that way. Each of these layers is a so-called green sheet. So it's white. Nowadays, most green sheets are blue, but this one is white. And you can imagine it a little like a booklet, yeah? We see it in a second. Okay, so imagine you have a booklet, and on the booklet, you have many pages, let's say 30 pages, and you print a pattern on each page. Okay. Imagine now that pattern would be electrically conductive. Yeah, that could be done. So you put them together, and in some way you have to sinter it to make it monolithic. On the other hand, then you would have individual layers, and each has a conducting pattern, but still layer to layer is not connected. So you need the vias. In the end, you have, let's say, different pages. Every page pattern comes from your CAD system, from your layout system. You have here some holes. These holes are just to keep it precisely on top of each other, because if you have conductors of 20 micrometers width, you also need an accuracy of below 20 micrometers in order to have matching layers. So that's, you print pages like for a booklet, yeah? And these are stacked precisely. And also you have vias. So that is from that laboratory in North Carolina. That's there, but just a manual laboratory. Nobody does it that way, really. You first have your green tape, which comes on a roll, like a big paper roll or so. Typical thickness is 0.1 millimeter and or 0.2. Then it is cut out to a certain size, and every sheet also gets these holes for the pins to hold it. Okay. In the next step, there is the stamping of the vias. That you must imagine a little like a sewing machine. There is a pin coming, but under that, let's say, needle that comes down and punches holes, the whole pattern is moved by a control system. And so all of the holes are punched. Yeah, of course, you always have a little sausage coming out on the other side, which is disposed of. And so the vias are stamped. Then the vias are filled, and that can be done by a screen printing process. In the screen, on the screen, we have only openings where the vias will be, and we put that whole that complete sheet of green tape on a table which has vacuum suction, and so the paste is sucked through the vias and filling the vias. So it's sucking them in, and so the holes are filled with paste. Of course, there must be a little more paste on top because it will shrink in the sintering. And so these vias are filled. Of course, that image is not done directly after filling, but after firing, because otherwise we could not prepare that for microscopy. But here we see how it looks. And after that via filling, we print the tracks. Again, that's the same process for printing conducting tracks, like in thick film technology. And in that way, for each layer, we get that pattern. Then all of the layers we want to have, so 1, 2, 3, 4 or more, they are stacked on these pins here. And they are pressed together. Again, that here is just manual production, just for showing. In the next step, that these green tapes are laminated. So you want to, in the firing, you don't want them to separate after the firing. What you don't want to have after firing is like having separate leaves of ceramic material, but they must be one monolithic body. And that can be achieved when you first press it at a slightly increased temperature. And in that green tape, there are polymers and there are waxes. And so it's somehow melting together. But not the ceramic is melting, but the additional material in that green tape. And so it is called laminating. And that laminating must be done. So you know, some bakery it delaminates, yeah, after, and for some bakery it just doesn't delaminate. You don't want to delaminate here. It should stick together well afterwards. So laminating is important. After the lamination, it can be cut. You must keep in mind it is a ceramic material, and these are some of the hardest material we can find. So we can still cut it to shape. Also, we can have rounded edges, and so what we don't need is cutaway. No, it shouldn't, because the lamination process should be good. Yeah. So it's a, normally that works well. Yes. Yes, you can. What experiment? If you have, let's say, 2 layers of wax, and you put and you make them warm enough and press them enough, you cannot separate them anymore. But in that wax, there are embedded many ceramic particles. So here it is cut. That works. After the firing, you cannot cut anymore very well. Then here they go into the oven, burning out organics. Now you can see the paste already changes its color here to, it was a gold paste evidently. And only after that, after all of the polymers are burned out, you can go into the firing. Because if you don't do that, and if you start sintering before all of that unwanted material is burned out, you have them trapped in, and that's not good, because that would lead to short circuit and the whole ceramic material would be black then. But if you do the firing in the next step, let's say at 850 degrees centigrade, you have a sintering, and sintering, we always know, sintering reduces porosity, and if the porosity is eliminated, the whole thing will shrink. So it becomes smaller. That is also a little problem in production. Why? Sorry? Yeah, but that's not the relevant point, because that's also in normal thick film. Also not, but imagine you put on a device like a surface mounted device. That device has a certain pitch, yeah? And when you fire and you reduce the size, for instance, it can shrink, let's say around 10%, yeah? That must be precisely, especially for big devices, because what happens if I have on the one side this pitch and on the other side this pitch? So it doesn't match anymore, yeah? And in that way, that shrinkage must be precisely. So again, that requires precise control. If we do wire bonding, it's not a problem, because a modern wire bonding machine, it is once programmed, and it is clever enough to look for the bonding site, not where it is programmed, but in the area where it is programmed. Then it looks with a vision system and it decides that's the middle of the pad, and then it bonds into the middle of the pad. So for wire bonding nowadays in modern technology is not a problem, because we have bonding which finds its bonding site. So that works fine. But if we have a device which has a clearly fixed pattern, like a surface mounted device, or if we would have, let's say, a flip chip device, yes, where also the grid of the balls is well defined, we must have the same grid spacing on the ceramic. And again, that shows us that is a process that must be well controlled. So that's such a tape. Here are again some of the examples we have. So here we have the shrinkage, let's say around 10 to 15%. It's a ceramic material. So it typically has a high permittivity or dielectric constant. Here it's around 8. On the other hand, the big advantage of these low temperature co-fired ceramics is that these can be modified as a material. So what you can do is, for instance, you can specify a material and produce it, which is having a low permittivity, having what is still more important, a low dissipation factor. Again, here 0.2% or 2 promille at 30 gigahertz. That's quite a good property, yeah, for high frequency application. And also here in that material, the CTE is lower than the CTE of normal alumina. So you can have special materials for special applications. For instance, one of my PhD students, he uses LTCC material, which is matched precisely to silicon. So in the range, for instance, let's say the silicon has, I think, 3.1 as ppm per Kelvin over that range, and the ceramic material has 3.2. Yeah, so that's how accurate that can be done. But I must say that was a special cooperation with a specialist we had here. There is one disadvantage of that marvelous material, that is the thermal conductivity. The thermal conductivity is only 3 watt per meter Kelvin. So do you remember what the thermal conductivity of alumina is? We had said it's around 20, 25. Yeah. So a factor of 10 roughly worse. Printed wiring board, a normal quality has 0.2. Yeah, that's still worse. But there can be tricks. What's the thermal conductivity of silver? It's 400. Yeah, let's say we have 1% of silver. That means 1% of 400 is 4. Just by 1% of silver in that LTCC, we increase the thermal conductivity from 3 to 7. Yeah, 1% of 400 is 4. 3 plus 4 is 7. So that's here. That's a thermal vias going through, and so that simple example shows us only 1% of silver more than doubles the thermal conductivity. So having only a little silver here going through with full through vias, then we can dissipate much more heat, and we can easily be as good as alumina material. So again, that shows us it's not only the material properties, it's always a combination of material and specific design that solves the problem. And so thermal vias are really important. And of course, thermal vias, you normally put them below the chip. What is the disadvantage? Of course, thermal vias will increase the CTE here because silver has a higher CTE than LTCC. Yeah. Yeah. Again, we fire in air, and firing copper in air will lead to a black powder and not to a conducting layer. Okay. So that's LTCC technology. Again, that's an example more or less we had from also from high temperature co-fired ceramic. There is one thing I would like to point out. That example here I took from some literature. It's not just for substrates, but also for packages. And what they were doing here is electroplated. Normally, LTCC doesn't have to be electroplated. The reason is that we already have noble metals. So if we would have some material like tungsten or molybdenum, then we need to electroplate. But here it's not really necessary. But the process for that is we have the green tape, which is extruded or cast, then it's cut to size. Of course, we punch here the registration holes. We punch vias, print into vias. We print the surface pattern. We laminate it. We first burn out organics and fire. So here that is shown as one step. Maybe I write it down here. And then we can have further processing. It's not only brazing pins, but we could also, for instance, solder on some pin in order to have a connector or such a thing. Okay, that's a profile of LTCC process. In the end, the high temperature profile is very similar to normal thick film technology, but here before we have to have a well-controlled heating process again. Okay. Here we see some properties. So typically we have line widths and distances of let's say nowadays 100 micrometers. So that means a pitch of 250 micrometers. And what is also important, what is the diameter of the vias we can achieve? And it can go down to 100 micrometers again. So that's much thinner than vias we have in printed wiring boards. And the minimum via pitch is given here as 200 micrometer. I think that sounds quite low to me, but the company specified it in that way. And that's a reason why we can have such a high wiring density. Again, what are the rules to have high wiring density? Fine pitch. Second is use most of the area for wiring, not for vias. Yeah. And the third is multi-layers. And in that way, we can have a high wiring density, and that is accomplished here. Let's say the printed wiring board technology initially had a lot of disadvantages. And one of the disadvantages in printed wiring board technology is that the conductor of a printed wiring board is not smooth. It is smooth on the top side, but it's not smooth on the underside because it's always somehow embedded into the polymer, and that's a result of the production process. So a printed wiring board has, if we have that conductor, on the top side it is smooth. For instance, we still have some nickel and gold on it, but that's the copper. But on the underside, it's not smooth. What's a result for high frequency application? And with high frequency, I'm talking about gigahertz or many gigahertz. What's the result? We have a damping, and there is so we have a lot of signal loss on the underside, because for a high frequency signal, which is mainly running based on skin effect on the surface, then we also need a smooth surface. But on the other hand, only the top side is smooth, but typically such a signal, as we have eddy currents, they would go somehow around that conductor, and in that way the damping is very high. So we want to have very smooth conductors. Also, a thick film circuit is not extremely smooth on the top side. Yeah, that's evident for multi-layers, but also on the top side, as it is a printed material, we still see, for instance, the screen pattern even after the firing. Also, there's always a certain roughness on a thick film circuit. And so people were seeking for the perfect conductor, which is as smooth as possible. And when you want to have a smooth conductor, the first thing you need is you need a smooth substrate. So in the end, a technology was developed where we use very smooth substrates and make very thin layers which have a low roughness, and typically such are sputtered layers. Also, in high frequency applications, normally we do not need thick layers, because the conduction always is only on the surface. And in that way, the main target is to have smooth surface for good signal propagation. And as I said, sputtering is a good process, but on the other hand, what are typical thicknesses we achieve with sputtering? Would you sputter 10 micrometer? No, never. That would take too long. And also the property is no longer good at such thickness. So sputtering is a typical thin film technology. And as I pointed out, thin film means 1 micrometer order of magnitude. So, and so mainly the high frequency people started developing thin film technology for multi-chip modules and for hybrid circuits. Again, hybrid, of course, we have, for instance, microcontrollers, or rather signal processors, ASICs on one hand, and on the other hand, we have high frequency transistors, which can be, what's a material for a high frequency transistor? Gallium nitride or gallium arsenide or such materials, but not silicon. So of course we cannot have monolithic integration. We must have hybrid integration on such a substrate. So what we can use as a substrate that is well available is just silicon. Silicon also has the advantage that silicon is very smooth when it is polished. Silicon also has the advantage, it is conducting heat very well, and it has a low CTE. So when you want to assemble another silicon chip or something similar on it, CTE mismatch is not a problem. Okay, so silicon can be used, but on the other hand, silicon must be insulated because it's never a perfect insulator, but so you need a layer of silicon oxide first to make it insulating. Again, that's also a disadvantage because such silicon dioxide layers cannot be made as thick as you want to have them. Typically, they are also only one to maybe several micrometers thin. And that means their breakdown voltage is also not so high, yeah, because maybe in such layers we have 100,000 volts per millimeter for 1 micrometer. That means it's breaking down at 100 volts. And that means it's not suited for high voltage applications, of course, but it's for high frequency. Then we can put on aluminum, and that aluminum is sputtered, and it is yes. How do we create the conducting lines of aluminum? So we first sputter it, and then I just want to hear one word that says it all. Photolithography. Huh? Okay. Put on a resist, pattern it, develop it, etch the aluminum, strip the resist, put on new silicon dioxide, put on a resist, etch the silicon dioxide, strip the resist, sputter aluminum again. Again, it's quite many steps here, but it works well. I once had a project together with a colleague from our business unit, and again, we didn't do it as a multi-layer. We just used silicon oxide and a layer of aluminum, and that was sufficient. Yeah, and then afterwards, for instance, we can put on a chip. We can put on that chip typically by adhesive bonding, because you cannot solder a chip to aluminum. You can also not solder a chip to glass or to silicon oxide. So you need another process, and a very well-suited process is conductive adhesive. So in that way, we can produce multi-layers, and as it is thin layers just stacked on top of each other, we do not need vias, but just by overlapping, we can we can come from one layer to the next. So that's the example which I mentioned. You can see here it looks a little black, but here is silicon oxide on it. Here we have aluminum conductors. Aluminum has also the advantage we can well bond with gold wires on it. Here we have the conductive adhesive. Here we have a chip capacitor which is mounted, and in that way such a circuit was created. And that was some very fast memory module we had produced here. Now, when we look at the individual layers we have here, so we see mainly two layers. One is the conducting layer and the other is the insulating layer. So in our example, we had aluminum and silicon dioxide, and that's typically a layer system which you use when you already have a semiconductor fab available. Yeah, because in a semiconductor fab, you always have possibility for sputtering aluminum, and you also have PVD processes or chemical vapor deposition processes for silicon dioxide deposition. On the other hand, it is a disadvantage because you put on the glass and then you have to put on a resist, you expose the resist and so on, and then you etch, and also how to etch the glass. So typically you do that with something like caustic acid or so, but probably for the aluminum you have a different etching medium, so both must be compatible if it's wet etching, so that's all not so good. So going to polymers has many advantages when we want to have these insulating layers. What is another advantage of using polymers as insulating layers? What kind of material is a photoresist? Is it ceramic, metal? What material is it? A photoresist. It's a polymer. Yeah, yes, we just, in fact, the material then is not called photoresist, but it's a photoimageable polymer. And the most important photoimageable polymer here is polyimide. So you can modify polyimide in a way that you can make a positive or a negative resist of it. And in that way, you do not have to put on the polyimide, put on a resist, expose the resist, develop it, and so on. So you can leave out the resist. You have a photoimageable polymer, and you just expose it and develop it. And you do not have to care about that etching and being compatible with etching of the aluminum and so on, but it's much more simple. And that's the reason why nowadays in making such thin film technologies, typically for the dielectric, we use photoimageable polyimide. So that's the most important possibility, but for today we are finished. And yes, let me say, sometimes I think you could make yourself a little more informed about generally about materials. Yeah. So because that is not a material science lecture, so it's mainly based on the idea that people know a little about materials. So the basic properties you already know, like permittivity, resistivity, and so on. So normally when I studied, we all knew these properties from experimental physics lecture. Yeah. So I normally I assume you also had that lecture, and these properties always have a dependency with materials. So it's better for the understanding if you're more familiar with the basics of materials. Let me say that. Okay. Yeah, there are. My best idea is, as you already know about which properties and what materials we have, like epoxies and so on, printed wiring boards and permittivity and resistivity and so I would say maybe you look for certain properties, and the best is just to look in Wikipedia for such specific information. Yeah. So again, when you see in the lecture notes, we have permittivity or yeah, dielectric loss factor or so. Maybe if you don't know what it is, maybe you should try to find out what it is. Yes, because that lecture is so complex. Yes, there are so many aspects of this lecture that I cannot really go into all of the basics. Yeah, because that lecture is made for people coming from many different backgrounds. Yeah, some never had material science in their background. Some, for instance, internals here who studied in Freiburg, they have had lots of material science. Yeah, that doesn't really mean they know more than the others about that, but in the end, I think it's an important thing, because you know that Devil's Fork has 3 peaks: materials, processes, concepts. Yeah? Okay, thanks for your attention. Okay, see you.